Welcome to our second part of our lesson on linear relationships. So, as mentioned before, we're going to discuss in this lesson the four different representations of a linear relationship. So, I would suggest that you copy this sheet if you're able to, print this out. But if you're not, I realize that this is going to be difficult to do along with me. However, what I'd like you to do is write the representation that we're talking about. The first one we're going to start in is graphs. We're going to do a proportional linear equations graph and a non-proportional linear equations graph. And so you won't be able necessarily to do the graphing with me if you couldn't print this out, if you can't print this out. But what's important is that you write down these characteristics as we go through them. And for the most part, the proportional linear relationship in equations we've already talked about in previous lessons. All right, so let's get started. As we look at this linear graph, we're going to notice, first of all, hopefully what we notice is that it's a straight line. So we're talking about in this the length of fabric and the cost in dollars. So yards in particular, if I bought 1 yard of fabric, it looks like it would cost $4. So the very first thing we want to write is that we notice there's a straight line. And since the word linear has the word line in it, that is referring to straight line. So both proportional and non-proportional linear relationships make a straight line. But the main part that's important about a proportional relationship is that the line starts right there, and that point is known as the origin. Okay, it passes through the origin. And if you're unclear what the origin is, it is a point on a graph, 0, 0. So 0 for the going the x-axis, starting at the x-axis, and 0 starting at the y-axis. So that's our starting point. Now let's compare what's happening with our non-proportional graph. And you may have noticed the line is not connected, but certainly we could make the line here, and it is indeed a straight line. So this linear relationship has a straight line. In fact, both of them do. This particular situation is talking about the number of tickets for the x-axis, and it's talking about the cost for the y-axis. So as we look at this, we see straight lines in both of them, but what makes this non-proportional is it does not pass through the origin. So we want to write that down. This does not pass through the origin. Oops, that should be pass, not passes. Let me erase that. What I do want you to notice also, and this will become important as we start discussing this, is it doesn't pass through the origin. However, it is a point, there is a point on this y-axis. In fact, this particular graph starts on the y-axis right there. And that point, if I look at this, the numbers I see are going up by 8. However, in between, there are marks, so that must be going up by 4. So we can guess that halfway between 16 and 4 would be, 16 and 24, would be 20. So this graph starts here at 20 on the y-axis. It's 0 for the x. I'm going to write that point, 0 for the x. It still stays on that y-axis, and 20 for the y. So now let's investigate what it looks like to have a proportional and non-proportional table. In fact, I'm going to try to move this so we can see the graph. there's a relationship between the graph and the table. In fact, if I have the graph, I can make the table and vice versa. So if I look at this first proportional graph, I'm going to notice that it starts at the origin, which means there's a 0 where the x is and a 0 where the y is. Right here is that point on the graph. The next point, if I move over 1 for the x, it's at 4 for the y. So 1 movement in the x and then matches up or corresponds with 4 in the y. The next point I see on the graph, if I move over 2 for my x and go upward, it's across from 8. So 2 corresponds with 8. 2 for the x, 8 for the y. And the last one we'll be able to put in the table. If I go over to 3 and look up, there's a point right there, and it corresponds with y as 12. So 3 corresponds with 12. So we can make our table from these points on a graph. And there's more points that we could do, but our table stops there. So here's what's important for a proportional relationship, which we already know it is because we have the graph to look at. A proportional relationship, when I look at the ratios between all of the y values divided by the x values or compared to the x values, I should get the same equivalent ratio, our same reduced value. So let's talk about that. The only one we can't start with is we cannot start with 0 divided by 0. This in math, if you put this in a calculator, it's going to say divide by 0 error, so we don't do that. We cannot divide by 0. So we're going to look at our second y value, which is 4, and put it over its corresponding x value, which is 1, and 4 divided by 1 would be 4. It reduces to 4. So we have that one. Our next, third xy pair would be our y value is 8, and we're going to divide it by our x value, which is 2, and again, that is 4. It reduces to 4. So now let's take our last ordered pair. We're going to take 12, which is the y, and its corresponding x is 3. Those two go together, and again, it reduces to 4. And if you recall from a previous lesson, we refer to this as the k value, and we also call it the constant of proportionality. In fact, it has the word proportional in it. See if I can fit this in here for right now. Constant of proportionality. So this is also known as a unit rate. So the characteristics we're looking for when we're talking about a table, when we're working with a table, is we're looking that all of the y divided by x values are the same. And we also can see that once we do divide those, we end up with a constant of proportionality. And I think I'll try to squeeze this in down here. So let's see if I can move this out of the way so we can work with the non-proportional table. So once again, we're going to be able to find what the table of values are just by simply looking at the graph. And we can tell it's linear because we see a line, but we need to know what those values are. So we mentioned a few minutes ago that at 0 for the x, it matched with 20 for the y. And then if I go to the next point I see on the graph, I see 2, and you notice this must be 1 in between, but 2 matches up nicely with 24. So we're going to put 2 and 24. The next point we're going to name is right here. and that point is right above 4, and that matches up with this point on the y-axis. And if I look, it's between 24 and 32. So what number is halfway between 24 and 32? That would be 28. And then the last point we'll be able to fit on the table is this point right here. I can see 6 as my x value, and if I look across, that matches up with 32 as a y value. So we've now been able to complete the table based on the graph. And vice versa, if I had the table, I could make the graph. So now let's test what we did last time and see if that also works for a proportional table, meaning we're going to check out these ratios, these y divided by x ratios. So once again, I cannot use this one because it has 0. I'm dividing by 0, and we cannot do that in math. We cannot divide by 0. So we're going to start with our second y divided by our second x, and we're going to get 12. So we have that one completed. We're going to go on to the third. I have 28, and that's divided by 4. And 28 divided by 4, oh, that would be 7. Not the same. Well, kind of curious. Let's try the next one. 32 divided by 6. And that is 5.3 repeating, and they are clearly not the same. So we can state in a non-proportional relationship or non-proportional table all of the y divided by x values are not the same. So we're going to write that those are not constant. But over here in the proportional table, they were constant, which led us to a constant of proportionality. And since we do not see a constant number here, there is not a constant of proportionality. There's one more thing I want to point out now on the table. There's 2 points that are important. If I look at the table, if I look at 0, 0 in a table, that's a great sign that I'm going to be starting at the origin. And so if I have a straight line that starts at the origin, I indeed have a proportional linear relationship. There's also another point that we're going to look at later on, and that is this point, whatever matches up with 1. In fact, maybe you can notice 1 and 4 were matched up here, and if you look, it turns out that all of these ended up being like the first one, 4 divided by 1. Over here, if we look at this point, this tells us right off the bat that this is not a proportional relationship because this is telling us that it does not start at the origin. So now let's continue with the next 2. We'll try to be brief for the equation and then the description. All right, so let's finish this up looking at the other 2 representations. We're going to talk about equation that is for a proportional relationship and equation for a non-proportional relationship. And if you, again, watch the other lessons, you've seen this before. In fact, we just got done speaking about a constant of proportionality, and that's also known as the k-value. And if we want to write an equation for this table and this graph, well, now we know what that k-value or constant of proportionality is. It is 4. So we could use this equation, y equals 4x, to make this table, and then we could make the graph. So they're all related. And I don't necessarily want you to be concerned the way that it's written. Unfortunately, linear equations are written what appears to be backwards. They give us the y first. We could write this as kx equals y, And technically, we could also write this because we're allowed, the commutative property allows us to switch order when we multiply or add. We could write it as x times k, because order doesn't matter when we multiply, equals y. But generally speaking, we're going to look at it in this form or this form. So now let's look at the non-proportional equation. You're going to notice there's a y in both of them. There's an x in both of these equations, a proportional, non-proportional, but this no longer has a k. And there's a good reason why it doesn't have a k. We did not find a constant of proportionality. All these numbers were different, where here we did. So we cannot use k. We're going to have to use another variable, and we'll discuss that has a special way to find that number as well. You're also going to notice that something's being added. We could also write this as minus b. So something's added or subtracted. And it turns out that this type of equation can also be written, if you prefer, we could switch the order. We could say that mx plus b equals y. And as mentioned, we could also subtract something from it. So the last thing, when we compare these two, this one does not add or subtract something to this equation, and this one does. By the way, when you have a number that is working with a variable through multiplication, that number is known as the coefficient. So m would be a coefficient of x, and k is a coefficient of x in our proportional equations. But this one adds a number, and this number that we're going to replace the b with is known as a constant. So coefficient would be an m because it works with a variable, and this one adds a number. It doesn't work through multiplication, so it's a constant. So now let's look at our very last thing, or last representation. We have a description. Mrs. Brandis bought 5 yards of fabric for $20. At this rate, how much would she pay for 12 yards? And it should have an S. And I want you to know that this description can go with this equation, it can go with this table, and it can go with this graph. In fact, often they start with a description first. You may notice, if you look at the graph, that if you look at 5 yards, it indeed matches up with $20. However, oftentimes we want to know what the constant of proportionality is. So from our lesson 2 weeks ago, we would take the money, which is our y value, and divide it by the yards, our x value, and we would indeed get our constant of proportionality. And then we could use this equation, y equals 4x, and this is how it's related. We could figure out how to answer this question. The y was the amount of money, so they're asking us how much. We don't know. We have our constant proportionality, meaning it costs $4 for every yard, and we're being asked about 12 yards. So we would be able to say that the cost would be $48. So again, if you watched our lessons a couple weeks ago, we did several of those type of equations. Last but not least, and I know this has been a long lesson today, you won't have any homework or anything else to do, but I do want you to have this information. We're going to look at the final description for a non-proportional relationship. Mr. Kaiser went to a theme park. He paid $20 to enter that park and $2 per ticket. What is the total amount he would pay if he purchased 12 tickets? Well, once again, if you look at the graph, the y is representing the cost. So we do not know the cost. So we're going to put unknown as y. It mentioned $2 per ticket, and x are the tickets. So we're going to multiply the number of tickets that we have by $2, and then it also mentioned that he had to pay $20 to enter the park. So this would be the equation that matches this particular table and graph that we worked with. So that's it for today. I will see you back tomorrow where we're going to delve into our non-proportional relationships. Take care.